All right, let's just jump right into this explainer. Today, we're talking about a surprisingly simple data structure that is honestly going to become your absolute secret weapon for acing technical interviews. We're looking at something you probably vaguely remember from your very first computer science class, the stack. But look, we aren't just doing textbook definitions here. We're going to break down exactly how to use it strategically. You see, the stack kind of gets overlooked, right? It just seems almost too basic. But the question we're answering today is, how does one simple data structure crack the trickiest interview problems? So rather than just dry academic theory, we're going to see how this incredibly efficient tool literally conquers some of the hardest algorithmic challenges out there in the wild. Top tech companies absolutely love testing your knowledge of stacks, basically because it shows you really understand how to manage data access dynamically. All right, level 1, core mechanics. To get there, let's treat this kind of like a video game. Think of this section as the tutorial level, where we just need to master the basic physics of our tool before we take on any boss fights. Now, the absolute crucial physics here is LIFO. That simply means last in, first out. Whatever item you placed on the very top of the pile, well, that's the absolute first one you take off. Just imagine a stack of plates at a cafeteria. You don't pull a plate from the very bottom, that would be a total disaster. You grab the one freshly placed right on top. And if you add a new plate, it covers the old ones. That physical reality is exactly how this data structure manages information in your computer's memory. Now, what makes these operations so incredibly powerful is just pure speed. We have 3 main operations here: push, which adds an element to the top; pop, which removes that top element; and peek, which just looks at the top element without actually removing it. In technical interviews, efficiency is literally everything, and all of these operations, they happen instantly, in O of one-time complexity. There's no searching through a massive array or traversing some complex tree. You literally just reach to the top, grab your data, and move on. That instant O1 speed is exactly why the stack is the perfect foundation for our first puzzle. Moving on to level 2, valid parentheses. Let's actually put these mechanics to the test with our first real puzzle. This one is a legendary interview question, and for really good reason. It perfectly isolates whether you actually know how to use a stack. So here's a concrete example question. Imagine your interviewer hands you a string of mixed brackets. An open curly brace, open square bracket, open parentheses, then a closing parentheses, closing square bracket, and closing curly brace. They want to know, is this string perfectly valid and closed in the correct order? Trying to solve that with a bunch of nested loops or counters, absolute nightmare. But with a stack, it is so elegant. Here is the playbook. Step 1. As you read from left to right, just push every open bracket you see onto the stack. Step 2, the exact moment you see a closing bracket, your brain should immediately yell, stack. So you stop and you check the top of your stack. Step 3, if the top of the stack is the matching open bracket, bam, you pop it off and just keep going. But if it doesn't match, or if your stack is totally empty when you see that closing bracket, the string is completely invalid. The stack basically acts as a perfect memory for the most recent unclosed bracket. Okay, level 3, the monotonic static. So you've mastered the basics. Let's actually slow down the pacing a bit here as we level up to a much more advanced mechanic. Honestly, this is where we separate the good candidates from the truly great ones. The word monotonic sounds super intimidating, I know, but the concept is beautifully strict. A monotonic stack just forces order. It requires the items inside to constantly maintain a strictly increasing or decreasing sequence. So instead of just blindly pushing every single item we see onto the top of the pile, we're now enforcing a strict rule. If a new item wants to go onto the stack, but it breaks our increasing or decreasing rule, we aggressively pop items off the stack until that rule is satisfied again. And only then do we push the new item. So when do we actually use this thing? Well, you deploy this specific strategy to solve really tough problems, like the next greater element. Let's look at another concrete example question. Imagine you're given an array of daily weather temperatures, and for every single day, you need to calculate exactly how many days you have to wait until a warmer day comes along. By using a decreasing monotonic stack, you just push the current day onto the stack. But the moment you encounter a day that is warmer, meaning it breaks that decreasing rule, you pop those colder previous days right off the stack and process them. That warmer day is literally the answer for all those popped days. The key takeaway here is you only process elements when the strict order is finally broken. I really want to pause on this quote for a second because it is incredibly true. The monotonic stack pattern is the hardest to see the first time, but once you get it, it clicks forever. It feels super counterintuitive at first, right? Popping things off the stack just to make room for something new based entirely on its value. It's the hardest pattern to recognize in the heat of a whiteboard interview, for sure. But trust the process here. Really study that daily temperatures example we just talked about, because once you finally get it, you will never forget it.
It kind of acts like a magic time machine, looking back at past elements the exact moment a future condition is met.
Next up, level 4, function calls.
Let's move to another boss-level technique and see how this builds into traversing really complex graphs and trees. We are moving way beyond just arrays and strings now, stepping right into the underlying architecture of your actual programming language. See, when you write a recursive function, a function that calls itself over and over to explore a tree, your computer's operating system actually uses a stack behind the scenes to remember exactly where it was before making that next call. So let's look at a concrete example. An interviewer might ask you to traverse a deeply nested file system just to find a specific document. Now, if your tree is incredibly deep, relying on the operating system means your program is probably going to crash with the dreaded Stack Overflow. So what's the solution? You take control. If you need to simulate a recursive depth-first search manually, building an explicit stock in your own code is exactly how you safely handle those underlying function calls. You push the starting node, pop it, process it, and then push its neighbors. You're basically just doing the operating system's job, but with way more control and memory safety.
All right, bonus level, the Java trap.
Okay, we've covered the logic, but before we wrap up this explainer, I really want to share an insider secret about language implementation that will very quickly separate the novices from the pros in an interview. If you happen to be coding in Java, pay very close attention to this because it's a major gotcha moment. Java actually has a built-in class literally called stack, so it seems completely logical to use it, right? Nope, wrong. Never use the legacy Java stack class. It's synchronized and it's slow. It literally adds unnecessary thread safety overhead to every single push and pop you do. Instead, you should always opt for the much faster, modern alternative, which is the ArrayDeque. Using that legacy class is basically a red flag to an interviewer that you might not be fully up to date with modern language performance standards.
So how do we actually write it correctly? Well, here it is. This is the exact syntax you should be writing on the whiteboard to properly initialize and use your fast stack in Java. You declare a Deque interface and instantiate an ArrayDeque. From there, your syntax is exactly what we discussed back in level 1. Stack.push x, stack.pop, and stack.peek. You get all of that beautiful O1 performance without any of the legacy synchronization bloat dragging your algorithm down. All right, we have covered a ton of ground today, from the core mechanics of LIFO to the elegance of validating parentheses, right up to the mind-bending logic of the monotonic stack and the sheer architectural safety of explicit depth-first search. Now that you have this incredibly powerful tool back in your inventory, fully sharpened and ready for modern coding environments, I want to leave you with this question to ponder before your next big interview. How will you apply the monotonic pattern in your next coding challenge? Seriously, keep an eye out for problems that ask for the next greater or next smaller element, because that is your trigger. Happy coding, keep learning, and I'll see you in the next explainer.